Hello and welcome. I'm Siladitya Khan from the University of Rochester. Today, the topic of my talk is modeling Bessel acoustic radiation force impulse imaging with the K-Wave MATLAB toolbox. First, the clinical relevance of the work here is tied to chronic liver diseases. Chronic liver disease in the US affects around 55% of the population. It induces liver fibrosis, which must be regularly monitored for its progression. Fibrosis usually leads to increased stiffness within the tissue, and hence ultrasound elastography can be a useful tool for monitoring fibrosis. Ultrasound elastography is a non-invasive technique for measuring biomechanical properties of tissues. The figure here shows an ultrasound transducer in imaging configuration trying to image the liver around some acoustic window inside the body. The ultrasound beam here propagates usually needs to propagate through a layer of fat and muscle to be able to reach the liver. Thus, it may lead to distortion of the ultrasound beam, which in turn leads to bad elastography images. In this work, we propose a new elastography beamforming technique, which we call as Bessel apodized acoustic radiation force impulse. In this In this figure, we show that focus beams can cause diffractive near-field scattering and hence leading to diminished depth of field. The Bessel apodized aperture over a linear array when compared to a focused push leads to better depth of field due to the absence of near field scattering and diffraction in as evident in the focused ultrasound push. We present a simulation pipeline for simulating heterogeneous digital phantoms in a MATLAB toolbox known as K-Wave. There are two parts to the simulation. First, in part A, we need to define the acoustic field, the properties of the medium. We also need to define the focused parameters of the focused beam, like the element size, the pressure profile, and the number of cycles and the center frequency that we want to image. These are usually set to values that represent parameters of a diagnostic imaging scenario. Next, we define the Bessel beam parameters, which are essentially the apodization parameters defining our acoustic radiation force push. Then we record the time varying intensity and calculate the acoustic radiation force push at every grid. The part A of the simulation ends here, and from where and the output of which goes into part B of the simulation, where we again define the acoustic field around the medium in which it propagates. We also define the, the parameters that we calculated from the previous part of a simulation as an input to this part of a simulation. Here we record the shear particle velocity of each grid and calculate the time delay using cross correlation methods. The cross correlation estimate gives us an image of shear wave speed. Figure A and B here shows that the elastograms generated from Bessel apodized acoustic radiation force push and conventional focus pushes. With Bessel apodized acoustic radiation force push, we observe that across all regions of the elastogram R1 through R4, we see an improvement of more than two folds in CNR and CR terms. CNR represents contrast to noise ratio and CR represents contrast ratio here. We also performed experiments on in vitro focal lesions that have been generated by mismatched elastic heterogeneity in a homogeneous medium. So in these set of images, we are trying to image using ultrasound uh, mechanical inclusion, which is of higher stiffness inside a lesser stiff homogeneous background. And we observed that with Bessel beam, acoustic radiation force impulse, we are able to preserve both the shape and as well as the estimate of stiffness of the elastogram within the elastogram. The panel of figures here show the comparison of elastogram quality of Bessel in comparison to multifocus supersonic shear imaging uh, scheme, which is the state of the art right now in elastography. And we report that across all imaging configurations, Bessel gives us the best preservation of the elastic heterogeneity as well as shear wave speed estimate. We also explored frequency dependent reconstructions in homogeneous phantoms. As you know, that as shear waves propagate in a medium, it undergoes wave distortion and dispersion as well as attenuation of also happens in the shear wave. In this work, we show that in an oil and gelatin phantom experiment, which is typically representative of a lossy medium in acoustic terms, we see better reconstructions of our we see better reconstructions of our elastogram in k-space. So the k-space energy intensity in spatial and temporal frequency shows higher bandwidth across the entire spectra. The pressure profile is consistent across depth, which helps us image deeply seated tissues, which may help us image deeply seated tissues in comparison to SSI. Thus, to conclude, we show here that Bessel acoustic radiation force can image at greater depth of field, show less near field diffraction. It has a high fractional bandwidth, performance in viscous mediums. The dispersion and attenuation reconstructions over extended frequency range is also seen in comparison to the state-of-the-art supersonic shear imaging. Thank you for your attention, and I'll take any questions.